Hi there. On the bench, another interesting piece of history. It may look like a resistance decade, but it is in fact a voltage divider. I got it very reasonably from eBay as it was no longer working. Let's see what the problems are and if it can be fixed. It comes from the early 1950s, and back in 2016, Low Z from EEV blog kindly posted its specs from a Muirhead catalog page from that time. The specs are actually quite good, plus minus 0.1% and a low temperature coefficient of 40 ppm per degree Celsius are not to be sneezed at. Sadly, page 6 is missing, so we have no idea about the AC performance. The box is made of teak with a metallized lining for shielding. Elsewhere in the spec it explains that this is a Rayleigh type divider and keeps the total resistance constant at 10,000 ohms. I had not heard of this type, but I am familiar with the Kelvin-Varley divider, which does a similar thing, so this could be interesting. Since it's a voltage divider, I connected a multimeter set to DC volts on the output and connected a 10 volt voltage from a bench power supply to the input. With all knobs to 0 or close to it, the output is already nearly 10 volts and it does not change when turning the knobs, so definitely not working. The eBay listing also mentioned a mechanical problem, and indeed the most left switch does not go beyond 4, no matter what you try. The next one works fine, but the one after that has exactly the same problem. You can't turn it beyond 4. And the most right one works fine again. That two switches have exactly the same fault at position 4 points to a common problem. Let's open it up. There are lots of wood screws to be removed, although some are missing. Most likely the previous owner left them out when investigating the problems. One screw in the top center position has broken off and is just spinning. Lifting the front plate and the broken screw comes with it. Getting the bit out that's stuck will be tricky, but anyway, that's probably a minor issue. Immediately it's obvious that someone removed the metallized lining from the inside. That's bad, but I could make a new liner from some aluminum foil. On first glance the resistors look not too bad. Nothing obviously burnt or melted. The switches look pretty corroded, which probably explains why my first test with the multimeter failed. The construction is reassuringly solid and looks modular. Each of the 4 switches looks very similar, and they all have 2 in and 2 out wires connecting them to the next switch. One of the input binding posts is directly connected to an output binding post on the other side. Interestingly, these are the top 2 binding posts, not the lower ones as one would naturally assume. Each switch has the same set of resistors on both sides, but from switch to switch they get lower by a factor of 10, from 1K on the left to 1 ohm on the rightmost. I decided to tackle the mechanical problem first, because if I can't fix turning beyond 4, the whole box is kind of useless. This is the switch on the most left with the problem. From the marks on the round brass contacts and the brass half circle, it is clear that this switch hasn't been turned beyond 4 for a long time. The slider part contacting the individual brass rods with the resistors on the other side is actually made of 3 separate strips. If you watch carefully, the problem is caused when going from the 5th rod to the 6th. The innermost strip falls into the gap between the 2 rods and then blocks turning the switch any further. Lifting the strip slightly out of the gap it has fallen in allows it to turn further, but the same problem happens again on the next position and so on. In this view, the rightmost switch is the one with the problem. Comparing this with the switch next to it in the same position clearly shows that the whole slider part needs to be further out. See how much of the rod remains visible on the right, while the slider on a working switch nearly covers the whole rod surface. I also noticed that the nuts holding the right slider assembly have no red thread lock compound on them, while there is some on the left. I wonder if someone was adjusting these before. Anyway, the way forward seems to be to undo the nuts again and push the slider part a little bit more out. Sounds easy, but this turned out to be a lot harder than expected. Although I did not thought I accomplished a lot of movement, it did the trick, and the switch now turned over all positions. So I added the nuts again and then tightened them. Onwards to the other switch, and yes, this one has exactly the same problem but on the other side, and I fixed it the same way. Let me quickly explain what these switches are doing anyway. One incoming wire goes to the first of the upper rods, which are all connected to each other using resistors with the same value. The other incoming wire goes to the lower rods that are also connected to each other using the same value resistors. One of the outgoing wires goes to the upper half-circle brass bar, and the other outgoing wire goes to the lower half-circle brass bar. If incoming on the right and outgoing on the left is confusing, the directions and switch order are swapped because I had flipped the whole front plate for convenience. There are two sets of sliders. The upper one connects one of the rods on its side to the upper brass half circle, and the lower slider does the same on the lower side. The upper and lower sets of sliders have no connection to each other. I made a little sketch to explain how this works. This is the switch seen from the rear. You have the rods, and I numbered them from 0 to 9 to indicate how they would be contacted depending on the position of the knob. In this drawing, the right side is the incoming connection and connects to the upper and lower rods respectively. The left is the outgoing side coming from the brass half circles. R indicates a resistor, and for a particular switch all resistors have the same value R, for example 1K. The blue line indicates the part that carries the two slider assemblies. In this drawing, the switch is in position 7. If you now follow the upper incoming path, it goes to the upper rod 9 through two resistors R in series, and then through the upper sliders to the upper rod 7 to the upper brass half circle and out on the left. The lower incoming path goes to rod 0, then through rods 1 to 7, a total of 7 resistors are in series. The lower slider then picks it up at rod 7, and it goes out on the left via the lower brass half circle. The result is that in position 7 you have a resistor of 2R on the upper side of the switch and 7R on the lower side, in total 9R. At any switch position, the ratio between upper and lower resistors changes, but the sum of the resistors in series on the upper and lower part is always 9. For example, if the dial is set to 0, we have 9R on the upper part and 0R on the lower part. If set to 9, it's exactly the other way around, 0 on the upper part and 9 on the lower. Putting it all together, we have 4 switches where the outputs of one are connected to the inputs of the next. The value of R for each switch from the left to right are 1K, 100 ohm, 10 ohm and 1 ohm. In this example, the first switch is set to 1, the second switch to 2, the switch 3 is set to 3 and the last switch to 4. This will result in the upper and lower resistance values shown. The sum of the resistance set on each switch adds to 9R, that is 9000 for the first, 900 for the second and so on. The most right switch is an exception because it has one more position. It can go from 0 to 10 while the others only go from 0 to 9. It works the same way, but the resistance value for the last switch always adds to 10R, and since R happens to 1 ohm, it means 10 ohms. If you now add the upper and lower resistances together, you get 8766 ohm for the upper part and 1234 ohms for the lower one. If I add these two values, you get 10,000 ohm as the input resistance, and that value does not change whatever the switch position. For example, if you put all the switches to 0, you have 9000 plus 900 plus 90 plus 10 is 10,000 on the upper part and 0 ohm on the lower. Why would you go through all this effort? Yes, a simple 10K potentiometer could do the same, but you would not be able to get reproducible settings of exact ratios. Apart from the mechanical problem, the other obvious issue of this divider is contact problems. This is particularly true on the brass half circles that are covered in some tarnish that is very difficult to remove. I worked on this for quite some time with contact cleaner and various other chemicals, and finally used a Dremel with a brass brush bit trying to polish the surface. I'm still not happy, but it works much better now. I will continue trying different cleaning methods to really get this as shiny as possible. This here is the most right last stage, using 1 ohm resistors and therefore most likely to suffer from contact resistances. I did not use rel on the meter. This was more about, do all positions make contact? But I'm still rather want this with less contact resistance. Anyway, at least you can see that this switch is special in that it counts not 0 to 9, but 0 to 10, and the resistances of the other side is the exact complement, 10 down to 0, so the sum always adds up to 10. Testing the input resistance, and it's clear that the resistance briefly fluctuates while a switch is moved from one setting to another, but after a setting is reached, the resistance is pretty constant, not quite the 10K, but about 0.4% too high. Testing the output resistance shows the expected behavior. The most left knob sets the resistance in 1000 ohm steps. The next knob does it in 100 ohm steps. And as you would expect, the next one does it in 10 ohms increments. And the last one does it in 1 ohm. With all this clear, what would I use it for? My idea was to use it for calibration or test accuracy of multimeters, especially in the high AC volts. I have no problems for producing a very accurate AC voltage with fine steps up to 3.1 volt, but from then on, fine and reproducible steps are a problem. I can, as shown here, produce a stable 100 volts AC or more after carefully adjusting output level pots, but I have to do that for every voltage, which is very time consuming. With the divider, I only need to set it for the maximum voltage, here 100.5 volts, because this is a demonstration. I did not spend more time in adjusting. Then I only have to dial in the desired fraction, say 0.1234, and I should see the voltage on both multimeters comparing their accuracy. Well, that works, but I'm not entirely happy. Given the 100.5 volts input, the red meter should read a bit more. Let's try DC using 10 volts as input, which is easier to get more exact. 10.005 is good enough. And after setting the output first to 0, I dial in again my 0.1234 ratio. The green meter is just for tagging along as an example of a meter that you want to check for accuracy. The output on the red meter is 1.2317, confirming that I'm seeing an output that is a little too low. Given the specs of the divider, I should see closer to 1.234 volts. I decided to measure the input and output resistances. The red trace shows the error on the output resistance. What I mean is, if I set the divider for example to 0.2, I expect to see 2000 ohm. When set to 0.03, I expect to see 300 ohms and so on. The graph climbs on the left, the low ohm side, as contact resistances play more role here, and the old problem that single-digit error percentages get more amplified the smaller the actual values are. The 10 ohm and 100 ohm switches are mostly in the 0.1% spec, but I'm rather disappointed that the 1000 ohm switch also shows an increased error. This is also consistent and slightly increasing across the whole switch range. This needs further investigation. The blue trace of the input resistance tells a similar story. It should be a flat line, ideally at 10K, which would be 0% error. Instead it's about 0.35% too high, but very flat until we get to the 1000 ohm switch. The only way to find out more is to measure each individual resistor as accurately as possible using 4-wire Kelvin probes. Here's the result. 4 graphs, one for each knob, so to say. Each graph has 2 traces. The red one I call upper because it's the top resistor in the standard voltage divider diagram in the middle. The blue trace is the lower resistor. There's also an orange horizontal line showing the 0.1% error limit. Immediately obvious is that except for 2 resistors in the lower part, all resistors in the 1000 ohm switch are pretty far out of tolerance. For 100 ohm it's kind of the reverse, just two upper resistors are outside tolerance, but look at the scale, the worst is just 0.16%, while the worst 1000 ohm is slightly above 0.45%. 10 ohms is mostly in tolerance and 1 ohm pretty much outside, but measuring such low resistances reliably is tricky, and besides these values have relatively little influence in the overall result, where the 1000 ohm part has much more of an effect. For this reason I decide to replace all resistors of the 1000 ohm switch. What type of replacement resistor is needed? Let's consider a simple case with a divider set to 0.1000. In this case, there's a single 1000 ohm resistor in the lower part and the resistors on the upper part add up to 9000 ohm. Lower and upper resistors together are 10,000 ohm. The divider was specified to handle a maximum voltage of 200 volts. With 10,000 ohms total resistance, this means a current of 20 milliamps flows through all resistors. That means the lower 1000 ohm will drop 20 volts, which is the desired 0.1 dividing ratio. Those 20 volts and 20 milliamps current causes a load of 0.4 watts that have to be converted to heat. Keep in mind that the upper resistor is in fact made of 8 times 1000 ohms that each have exactly the same load. Given that I need to get 0.1% rated resistors, that's a lot of power and very expensive resistors. To stay affordable, I have to limit myself to 100 volts maximum input. Redoing the calculation results with a load of 0.1 watt, still a lot for precision resistors. Just to finish this off, as this table shows, with 100 volts at the input, the 2 times 9 resistors together will dissipate 9 times 0.1 watt at any time, regardless of the switch setting. The switch setting only determines which of the resistors will be lucky and stay cold, but for each resistor it's either 0.1 watt or nothing, no in between. For my new resistors, I picked the CMF60 type with 0.1% tolerance from Vishay-Dale because it was affordable. The power rating is 1 watt at an ambient temperature of 70 degrees Celsius and 0.5 watts at 125 degrees. That is 158 and 257 degrees Fahrenheit. The temperature coefficient is slightly worse, only 50 ppm compared to the 40 ppm in the divider spec. I think I can live with that. But if you drive a resistor hard, its specs will change irreversibly. This is where the second table comes in. At 70 degrees ambient, if I drive it with up to 1/4 or 0.25 watts, I can expect a shift of 0.15%. Well, I'm planning to use only 0.1 watt and I hope the ambient temperature will never reach 70 degrees even though the enclosure has no ventilation. This, by the way, is probably what happened to the original resistors. The 1K resistors are the most stressed in this divider because they drop the most voltage, and I could well imagine someone running this at 240 volts AC instead of the maximum 200 volts. The original 1K resistors look like this, so my replacement has to be compatible with this arrangement. Two boards form the lower side of the switch, the same arrangement is on the other side, the upper resistors. One board carries 5 resistors, the other one 4. The split into 2 boards is needed to fit the round switch. The way whole sets of resistors are made by these boards make it very hard to just replace 1 or 2. So for my repair I decided to replace all 18 resistors and follow this arrangement closely. My carrier is made from Vero or strip board with a strip spacing of 2.56 mm. Every fourth strip was extended with a 1 mm diameter copper wire. Small links connect the inner strips to the ones with a copper wire extension. On the inner strips the resistors are soldered in, which makes them slightly slanted, but I don't mind that. I show this here as a sketch because somehow I have no good pictures on how my replacement boards are designed. Here's one good last look at the old 1K resistors. I decided to snip them out because First, for desoldering from the switch and later to resolder my new ones, I would need a very strong soldering iron, and that heat would also melt my solder joints on the strip board. Instead, I will solder my boards to the stumps left by my surgery. Of course, the boards you see on the bottom will also have to go. Here's my first replacement board soldered on the stumps already. You notice that I arranged the resistors to stand clear of the board to give them the best cooling possible. Now I have to fix the second board on the lower portion of the switch that, like the original, carries only 4 resistors. And by the magic of YouTube, here it is in place. I still have to repeat the same process for the other side of the switch. Applying 10 volts as before on the input and selecting again a ratio of 0.1234 now shows a much more accurate output. So, mission accomplished. This is confirmed after I repeat the measurement of each resistor in the 1000 ohm switch. Compared to the old resistors, the new ones now nicely stay just under the 0.1% tolerance. And the same effect is now also visible on the overall input and output resistance graphs. Apart from the very low end, the divider now meets the 0.1% spec for the whole range. And, somewhat accelerated, this is a thermal image of a part of the upper resistance board when applying 100 volts AC. The setting was 0.1234, but the lower resistors do not even register on the thermal camera. Over time, the temperature settles to just below 42 degrees. That is of course outside the box with much better airflow. And on the lower side we have a lone single resistor as it should. The temperature appears to be a bit lower, probably because there are no neighbors heating it up. I did run a test with 100 volts and the divider in the box with a thermocouple inside, close to the 1000 ohm switch, and over 45 minutes the temperature increase was not even 2 degrees Celsius, so I don't think I have to worry if I stay at my 100 volt limit. Remember the metallized lining that was promised in the 1950s catalog? Well, there are actually some traces of copper colored paint in places, and testing reveals that this paint is conductive. Unfortunately, it has worn away, so there's only patches and they're not connected to each other. Although I'm planning to use the divider with higher AC voltages, so shielding may not be so important, I think it's just good practice. I use kitchen aluminum foil to create an inner layer which hopefully should do the job. Incidentally, I tested the divider with my new resistors at various frequencies, and going up to 100 kHz is fine without having a noticeable effect. The last question you may have is, what's the difference between this divider and the much more popular Kelvin-Varley divider? From the outside and usage there's no difference. They behave exactly the same way and both have constant input resistance. Inside they are very different in the way the switching works and the resistance values. If you want to know more, there's a Wikipedia entry on it from where I also took this diagram. The Kelvin-Varley schematic shown in the article provides the same functionality as my divider, but uses an input resistance of 100K instead of 10K. But you can easily recalculate it for 10K input resistance. The Kelvin-Varley is more popular because you need a lot fewer expensive precision resistors. In this table I sum up the number needed for a 4-stage divider. Kelvin-Varley needs just 43, whereas my divider contains 74 for doing exactly the same job. So why would anyone build a divider that needs nearly twice as many expensive resistors? I think the answer is in the second table. Muirhead was building a lot of resistance decades. For these you need a lot of power of 10 resistor values. In other words, they had a well-established production line going that produced tons of precision 1, 10, 100, 1000 ohm and so on resistors for their decades, which just so happens to be exactly the same ones needed in my divider. To make instead a Kelvin-Varley divider with 10K input resistance, you need 1K, 200 ohm, 40 ohm and 8 ohm resistors. Apart from the 1K, all the other values would need new production facilities. My guess is that for Muirhead, making a divider that needs 74 of their standard in-stock resistors made a lot more sense economically than a divider using only 43 resistors, but of which 32 are special non-standard values. The Muirhead divider is now part of my test equipment inventory, and I will use it in the future to speed up checks of multimeters and the like. Please contact me if you have an interesting piece of equipment that you want to send in for review or repair, or if you want to donate it to the channel. If you enjoy my videos, don't forget to like and subscribe. There are many more projects, repairs and reviews coming up, and it would be great if you decided supporting this channel by becoming a Patreon. Thanks for watching.